seated. Good evening, ladies and gentlemen. It's my pleasure to welcome you to this inaugural lecture this evening. I would like to welcome very specifically the Vice Principal, Research, Innovation and Postgraduate Education, Prof. Sunil Maharaj. Our speaker, obviously, this evening, Prof. Tinus Stander, members of the UP Executive, Deans and Deputy Deans, Prof. Raj Naidu, the Head of Department of the Department of Electrical, Electronic and Computer Engineering, as well as the other heads of departments that are present, our academic and professional staff, colleagues, family of Prof. Stander, specifically, ladies and gentlemen, and I would like to say students also, although you may be seen in some ways as almost colleagues, but it's important to be here. It's really a wonderful opportunity for us to host these inaugural lectures. And Prof. Stander will this evening talk about making big waves with small waves, today's challenges in microwave and millimeter wave engineering. And I would like to request Prof. Sunil Maharaj, who officiated this evening's inaugural lecture, to join me and to open the event and do the official welcome. Thank you.
Professor Tinus Stander, and of course his wife, Dr. Elsa Marie, and family. Professor Wynand Steyn, our Dean of the Faculty of Engineering, Built Environment and Information Technology. The Deputy Deans, the HOD, Professor Naidu, of course members of the faculty itself, as the chairs of schools are here, some of the HODs are here, and of course members of the University Executive, our industry colleagues, as Professor Steyn said, our students, our postdoc students, wonderful to have some of you and researchers, and of course members at large. Good evening, welcome, wonderful having such a number of smart engineers in the house. A word of welcome to each and one of you on behalf of the University of Pretoria. I think among the many engagements that I have as Vice Principal responsible for research and postgraduate education, I think inaugural addresses are one of our professors is always something I think to look forward to, and it is, of course, it is a celebration of a colleague having progressed to the highest academic echelons one can have at a university. But it is also an opportunity to be addressed by someone at the cutting edge of a discipline on the latest research in their field. Often an inaugural address presents research that has not yet been published, and or so one is given the glimpse into the future, sometimes in the field of interest vastly different from one's own. And I think it's also a learning experience for many of us when we attend these events. I think that is, however, not the case for this evening, as you may know that I have strong ties with this academic department, having come from there as an electronic engineer myself. And I think it is therefore a special honor and pleasure for me to have been asked to officiate at this occasion. Ladies and gentlemen, in our digitally connected world, the position of the university at the top of the educational pyramid can no longer be taken for granted. Among the factors that play a role when considering the continued relevance of universities in a growing mistrust in academic expertise and knowledge production, the internet has made everyone an expert, as we may be familiar with. Furthermore, opinions informed by costly and time-consuming research must compete in social media, as I'm sure we all experience that, with views of rogue experts and fake news. And sometimes people think there is a few points from internet and they're the expert in that area. And that's why we need to continuously move the field of science and have science informed, or things informed by good science. Added to this is the persistent perception that universities are elitist and exclusionary on the one hand, while on the other they are viewed as sites of political contestation that many would rather avoid. Furthermore, the universities and the world over have to increasingly operate under tough conditions like reduced state funding, economic pressure, and of course other political pressures. There are, however, many reasons why a university education remains sought after. These include the physical spaces and facilities that traditional universities like UP offer, laboratories, maker spaces, music conservatories, art and architectural studios that support the academic project and, of course, provide students with an opportunity for hands-on experimentation in the chosen field. Of course, universities not only offer academic facilities, but also a wide variety of cultural and recreational facilities that provide students with the opportunity to experience all aspects of student life and a real sense of community. Coupled with high-quality qualifications, the all-round formative experience we offer to students sets universities apart from other educational alternatives. In his book, I quote, "The Soul of a University, Why Excellence is Not Enough," close quote, Professor Chris Brink argues that a crucial question is not merely what universities is good at, but also, more importantly, what it is good for. This is not a new question for the University of Pretoria. Our vision captures how important we regard being relevant and making a difference both locally and globally. The University of Pretoria makes a difference in countless ways, but at the heart of our impact are two key elements, namely the graduate attributes and what we deliver and the research we produce. And both these aspects are fully dependent on the kind of scholars the university attracts. As our most highly esteemed faculty members are experts in their fields, our corps of professors are the vital link for enabling the manifestation of a university's ideals as they are captured in our vision through teaching and learning and research within the academic departments. They also drive our engagement with the external environment through collaboration with the peers, both locally and globally, but also with government and industry partners. Professor Stander, the topic you have chosen for your address this evening, making big waves with small waves, today's challenges in microwave and millimetre wave technology, is catchy, but also a very appropriate reflection of the impact that research in your field makes. You clearly demonstrate how research in your field is transdisciplinary by its very nature, thanks to the virtually unending list of applications for microwave and millimetre wave technology. We look forward to your presentation on how the latest research is aimed at addressing challenges specific to some of these applications. We like to refer to the University of Pretoria as a future-focused university, and it's a priority for us to ensure that our students are ready for the future world of work. However, in a rapidly changing world, the future is an elusive concept. As the audience, we therefore look forward with anticipation, Professor Stander, to the conclusion of your address, where you promise to provide us with some insight into the challenges the next generation of microwave engineers can expect to face, and into the research that might assist them with overcoming these challenges and some of our societal and economic challenges. Ladies and gentlemen, I think you will agree with me that there is every indication that we look forward to a more stimulating and interesting address by Professor Stander this evening. First, however, it is my pleasure to introduce him to you. Tinus Stander is a professor in the Department of Electronic and Computer Engineering. He completed both his undergraduate and PhD studies at the other university we call Stellenbosch University. After completing his PhD in electronic engineering in 2009, he spent 2 years as a radio frequency and microwave engineer at Denel Dynamics. He then started his career as a senior lecturer in the department at University of Pretoria in 2013 and was promoted to associate professor in 2020. Tinus was awarded the Erasmus Mundus Euro SA Scholarship in 2013 and received both his NRF rating and Sandal B category researcher rating in 2020. He has authored or co-authored something like 27 journal articles and is author of co-author of 52 international conference papers. Prof. Stander also holds 3 patents. His supervisory track record includes the completion of 8 master's students as well as 6 PhD students. He is currently supervisor or co-supervisor of 8 master's and doctoral students and 1 postdoctoral fellow. Tinus is registered as a professional engineer with the Engineering Council of South Africa and consultant to the South African National Road Agency, SANRAL. He is a scientific advisor to Multifractal Semiconductors Pty Limited, as well as a senior member of IEEE. He has been a member of many technical committees and involved in many conferences both locally and internationally. Prof. Stander is a reviewer for several journals, and prestigious ones I might add, including the IEEE Transactions on Microwave Theory and Techniques, the IEEE Microwaves and Wireless Components Letters, and the IEEE Electron Device Letters. Prof. Stander's research interests include millimeter wave microelectronics for terrestrial communications, built-in self-testing of RF and microwave electronics, millimeter wave radiometry for radio astronomy, and he works a lot with the SKA team, millimeter wave remote sensing for transportation applications, as well as additive manufacturing for microwave and millimeter wave components and packaging. Ladies and gentlemen, it is my honor for you to join me as well to welcome Prof. Stander to the podium to deliver his address. Prof. Stander.
Mr. Vice Principal, Dean, Deputy Dean, colleagues, friends and family. Welcome to a brief introduction to things that keep me up at night. The challenges facing microwave and millimeter wave engineers today, and the challenges I envisage for the future for them, and how I've worked over the past few years to help address these challenges. Just a brief overview of my presentation. I'll start with an introduction to microwave and millimeter waves and their applications, and then I'll take a thematic stroll through my research career for the past few years, zooming in on a few specific problems that myself and my collaborators and my students have looked at over the past few years, and how we've made a contribution to those challenges. I'll conclude with a few future endeavors, things we aim to look at for the future, and then of course conclude with some acknowledgements, because many acknowledgements are due tonight. I think most of us are familiar with the concept of a radio wave, this magical link through the ether that makes our remotes open our garage doors, or connects us across the world to loved ones via telephone. But there's a wide range of radiations we can look at in the electromagnetic spectrum, all the way from the low radio waves up to visible light, ultraviolet, X-rays and gamma rays. Now, although it's a continuum of radiation, the techniques we apply there are very different. Many of the design techniques that we work at here in long waves and radio waves do not work at even microwaves, and certainly not at millimeter waves. The challenge is to decide which techniques work where and how these translate to feasible applications. That's where most of my research has been, especially distinguishing between microwaves and millimeter waves. I will refer to 2 key concepts tonight. The one is frequency, the other one is bandwidth. Frequency is where on this electromagnetic spectrum do we operate, and bandwidth is how much of that spectrum do we need to occupy for a specific application. And the 2 key trends are always we're moving up in frequency and we're occupying more spectrum. And I'll explain why when we get to the applications. So what are microwaves and millimeter waves used for? The most ubiquitous application, no doubt, is communications. We walk with it in our pockets, we see it when we watch television. We see all the logos, LTE, 5G, GSM. So terrestrial communications and broadcasting is a primary application for microwaves and millimeter waves. Millimeter waves more so with next generation communication systems such as 5G. We can also use microwaves and millimeter waves to build an image of the world around us. The classical example is radar, where we illuminate a scene or a target. We look for reflections from that target, and we can tell something about it, whether there is something or not, where it is, how fast it's going, how big it is. We can also use other spectral wavelengths to build other kinds of images. For instance, the use of these airport security scanners to build body images for security purposes. As we can build an image of the world around us at different wavelengths, so we can build an image of the night sky or just interstellar space, also with a variety of wavelengths. We can use optical astronomy to see stars with visible light or infrared, but we can also use radio waves to build images like this, which was recently produced by Meerkat, which we cannot perceive with the naked eye or with infrared wavelengths. So contributions to radio astronomy and SKA and the Meerkat project are also part of my talk tonight. And then there is something that's not quite as well known, but equally important, is passive radiometry or remote sensing, where we put up highly sensitive detectors to measure passive emissions from the environment around us. And we can tell many things from it: ocean salinity, ground cover in broad regions with satellite imaging, building an image of the atmosphere and gas concentrations. And I'll talk about that more when we get to water vapor radiometry. Other ubiquitous applications are location and navigation, like the very well-known GPS system. Heating, of course. I think most people will be familiar with this application. I think few people will be familiar with this one. Same principle, different frequency. This cooks your dinner. This burns a protester. It's a direct energy weapon developed by the Americans. It works at 95 gigahertz, burns the skin, doesn't cook the organs. Reasonably safe, I suppose. So, I don't work in dielectric heating. And then there are, just to finish off, non-propagating wave RF applications. There are wireline applications as well. I won't go into them tonight, but non-propagating wireless communications we see on a daily basis is RFID tags that you use to tap your bank card to gain access or to make a transaction, or of course wireless charging. I mentioned two trends in my opening slide. The one is going to high frequencies, and the other one is occupying larger bandwidths. And that creates many challenges for the microwave and millimeter wave engineer, especially handling wide fractional bandwidths. Because whether you work at a very high frequency or an extremely high frequency, you can always down convert that spectrum to a lower frequency to process it. But the problem is, if you have wide bandwidth, you have wide bandwidth of data. You need to digitize it. You do get analog to digital converters, which is a circuit we use to convert analog data to digital data, but the wider the bandwidth, the more power they consume, the more expensive they become. The other problem is, of course, that having lots of digital data means you need to process lots of digital data, which puts a severe strain on your digital backend for your application. This is especially true in an application called beamforming, digital beamforming in particular, where instead of having a broadcast antenna like we used to for cell phone towers, we steer a beam from an array of antennas electronically to where we need it. Now, digital beamforming is a way to control these individual antennas to form the beam to point in a specific direction. But again, processing that very wide spectrum of data for each individual antenna element becomes a challenge. So early on in my career, I asked myself, and of course I asked my students, can we process or manipulate broadband microwave data before we digitize? And we've made a few contributions there. The first thing we realized is that you can build up a second order all-pass network, which is a very old classical network, to approximate any delay function. We were focusing on delay functions for the beamforming application. To approximate any delay function you want to using an actually very simple low-order network. And the key to synthesizing these networks within an arbitrary equiripple error is to start with a good analytical approximation of your problem. And you get that your solution converges much faster than with classical genetic algorithm methods. So armed with the synthesis method, we ask ourselves, well, can we implement these networks? And we came up with two iterations of the circuit. So the one we implemented in 0.35 CMOS. There you can see there's our delay curve we implemented, and there's the peak at about 70, 80 megahertz. And most of our innovation actually did not go into the circuit itself, but it's these second generation current conveyors, which were notoriously difficult to stabilize. So much so that we got a patent just from a stability analysis of that current conveyor. We also demonstrated the first millimetre wave dispersive network, second order network here. A fairly high delay peak of 62 picoseconds at 36 gigahertz. It remains to today the only practical implementation of that circuit we found in literature. We also looked at moving back to analog beamforming with phase shifters, and how do we tackle the problems that digital beamforming could solve previously, namely very wide bandwidth and dispersive phase shifting. In an analog sense. So we've also developed dual band phase shifters. This one gives you dual control at 2.4 and 5.5 gigahertz for Wi-Fi applications. And we've also developed a very wide band, almost full X band phase shifter using a single metallization layer. It doesn't seem like an important point until you realize that a single metallization layer is all you have in a typical gallium arsenide or gallium nitride microelectronics process. So although the printed circuit board implementation might not be that impressive, the principle that we illustrate here is very important. Moving on to a related field. The need for higher bandwidth and higher frequencies means that we move more and more to integrating as much of our microwave and millimeter wave system on a single integrated circuit, as is evident from the largely ubiquitous RF systems on chip we find these days for modern applications. There are many things you can do very well on the chip. Amplification, very easy. It's the best way to put it. You don't amplify with discrete components, not with these frequencies. Mixing, similarly. Detection, definitely. But it's notoriously difficult to move signals around a chip, and it's extremely difficult to filter them. So these are very complex interconnects we have to deal with, and they're very lossy. And you need to model them accurately because you need to know what this loss is before you prototype. Otherwise, your design will fall short of specifications and you need to respin chips, and these are very expensive to make. So you want to get first iteration success as far as possible. So we ask ourselves, at some point, can we put good millimeter wave filters on chip, because we haven't seen any? And can we do better with moving these signals on chip? So we spent a lot of time on designing new design flows for modeling millimeter wave interconnects on chip and their transitions. And we came to a design flow which used the now industry standard finite element method to model interconnect, but in a hybridized fashion where we can do first iteration tuning with a combined RC parasitics extraction to extract the resistance and capacitance of the interconnects on chip first, to get sort of a ballpark idea before we commit to final sign-off and fine element methods. We also found that integral methods were lacking in this regard, which was a surprising result because they showed great promise at lower frequencies. We've also looked at the optimal impedance for routing slow wave lines on chip. Slow wave structure is a kind of on-chip transmission line which maximizes the amount of phase shift for a specific length. And what we found was that if you choose a non-optimal impedance, something like 25 ohms or 30 ohms, you get a much better phase shift to insertion loss ratio or Q factor than what you got if you chose the standard system impedance of 50 ohms, which makes sense because there's no reason to interface to 50 ohms in a chip. The only point where you need 50 ohms is where you interface to other system components off chip. We also demonstrated two critical building blocks for millimeter wave on-chip filters. The one was active Q enhancement, where we could take a passive resonator on chip with a Q factor of 15 and actively enhance it to get a Q factor of, well over 1,500 at 80 gigahertz. And any filter designer will tell you you can't synthesize a sensible, reasonable filter with a resonator Q of 50, but a couple of 100,000, you're talking about very low loss, very highly selective filters. And this design, also one of our patents, now enables that design. We also experimented at some point with notch filters at millimeter wave frequencies on chip, and we could demonstrate, in this case it was a dual notch filter with a reflectionless architecture over here. So we can demonstrate that reflectionless filtering on chip is also possible. Moving on to something rather different. We took an interest in 3D printing of RF components some years ago for many reasons. And the main reason, or one of the reasons at least, was that prototyping is much, much cheaper. So it's much easier to go through fast iterations of prototyping with 3D printing. And that's one of the values of it. I'm a big proponent of new technologies, obviously, from the nature of my work, but it has to serve a purpose. And I've spoken on this topic to many audiences. 3D printing is a valuable technology if it is applied with purpose. And I see the role of 3D printing summarized here. Number one, it is a rapid prototyping tool. And it is a rapid customization tool for small-scale production. I don't see 3D printing as a volume production tool. It will never compete with an assembly line. But in a specific instance, where it's applied in low batches for rapid customization, yes, it serves a value. The other purpose it concerns is very complex designs. There's a saying in 3D printing that complexity comes for free. You often have manufacturing considerations in these RF components. You have to ask yourself, well, this design will work well, but can I machine it? And very often the case is not, at least not as a single component. You have to break it up into separate components and assemble it. And every time you have assembly, there's room for error and there is delays. So in 3D printing comes for free. There's also an industrial reason for 3D printing, and that is lowering the requirements on supply chain, where you can produce components at the plant. This is opposed to FDM printing, extrusion printing, which most of you should be more familiar with, where you have a nozzle of material which you locally melt and move around. So why did we choose this? Well, we firstly chose either FDM or SLA for the plastics printing because they're cheaper. The materials are cheaper, the equipment is cheaper. So it's a more sustainable way to do volume of prototypes for research. Why SLA over FDM? A couple of very important characteristics. It has higher resolution. than FDM typically. The dielectric material is more isotropic. You can see here from a SEM image, that's a fairly homogeneous dielectric film that you get from an SLA print, but with large air gap inclusions in FDM. So that's something we want to stay away from. The other thing that's shown here is that FDM is more porous compared to SLA, so low ingress of materials if you want to post-process. There is a drawback to SLA, and that is that there are fewer good materials, 3D printing materials for photopolymer vat resins compared to filaments. You get extremely good RF filaments in practice, and that is one of the drawbacks we have to navigate. There are many challenges in using this technique for component printing. The first one is, do I use my 3D printing as a structural component where I plate it in metal inside and out, and where my interaction is only metal and air, much like a metal printed part? Or do I include the plastic into my functional design, where I have a complex interaction of metal, plastic and air to create my functionality? And then there are, of course, the considerations you always have. How do I improve the resolution? How do I reduce the cost? And how do I reduce the loss? And then a particular one we found out very early in our exploits is that it's a particular challenge to plate smooth, porous 3D printed parts with simple, non-toxic processes. And a lot of our early work went into establishing that. So we were driven by, again, questions. Can we make 3D printed microwave and millimetre wave components better and cheaper? Can we use 3D printed materials as functional elements? And that is a very active area of research in my lab currently. Our first contributions were in structural use, where you print a plastic part, you plate it in its entirety, and as far as the electromagnetic waves are concerned, it's a metal part, because the waves only interact with your metal surface. They never penetrate into the plastic. We came across a method called the tolerance reagent, which is an aldehyde test. It can be used industrially for mirror making. And we found that it was often used to create a seed layer on these parts for subsequent copper plating or electroplating of other metals. And we asked ourselves, well, can't we just repeat the process a couple of times to create a good conducting surface? The answer is yes, you can. Repeat it 4 to 6 times, you cool down the solution just a little bit, you get a response that compares, the response in red, which compares extremely well with an off-the-shelf component. And in this case it was a brass extruded waveguide, and compares even better with the metal printed waveguide of the same length. And then we wanted to demonstrate this new technology by producing a component that actually has value. So we decided on a squint-free antenna array, where we had a series-fed array here. There's a 4-element Bohr array, and you can see the center, the Bohr site here changes very little, from 21 to 26 gigahertz. Remember I said previously 3D printing must serve a purpose, and the purpose we wanted to show here was the internal corrugations that we could not machine, we could 3D print. So if we wanted to machine this, we had to do a split block assembly and incur extra assembly time and cost and potential errors if we did not 3D print it. So again, we demonstrated an application where the 3D printing actually has value to the design. The first step in using these materials in functional designs is characterizing of the materials themselves. And something that we struggle with and our collaborators at TU Eindhoven struggle with is that the classical methods to characterize these materials at high frequencies scale with wavelength. So where you had a reasonable sample size to work with at microwave frequencies, it becomes a nearly impossible sample size to work with at millimetre wave frequencies. So defining new ways to characterize this material where you can work with just physically larger samples was one of the first things that we did. And I worked on a new method using a differential group delay measurement on two otherwise identical samples of different lengths, deriving some knowledge that we gained from de-embedding transmission line measurements in microelectronics. So porting some of that background to a new domain. And what we find is that the method currently still underpredicts the dielectric constant just a little bit, but the consistency of the data we get in predicting the loss of the material is exceptional. Much better than the classical methods. This is the Nicholson-Ross-Weir method. You can see there's a large variation in the predicted loss over the frequency band, whereas the differential tau method gives you a very smooth, even response in loss estimation. Of course, after that, once you've characterized the material, you need to apply it in the design. And one of the simplest ways to metallize a design around in this case, a microwave filter, is to buy your metallization, ascribing no customization to it. So we experimented with two different designs. One is coupled singlets and doublets, and the other one is a stepped impedance low-pass filter. And in both cases, we found that we could print a custom insert into an ordinary off-the-shelf waveguide and create a filter as a result. Both of these working in K-band, this one with a bandpass frequency of 22 gigahertz, this one being a low-pass filter also at K-band. And we believe this is an interesting new design paradigm for rapid customization and rapid changes in waveguide-based systems going forward, if we can get better materials. But there's light at the end of the tunnel. We've already spoken to some of the manufacturers for these materials, and there are good materials now coming into the market. I mentioned earlier that in 3D printing, complexity comes for free, and we demonstrated that in one of our earliest works, where we 3D or metal printed a interdigital filter here, and we couldn't figure out how to machine these triangle coaxial lines, because you can't machine them from the top. The cavity is, or the line is too deep, the cavity is too deep, so you can't drive a cutter in from the top, and you can't cut it from the side, this angled surface from the side either, because you'll have step discontinuities. So, because we had 3D printing, we could print an arbitrary, complex geometry, we could realize this filter. Something that we started looking at in service of radio astronomy in South Africa was water vapor radiometry. Why is water vapor important? Water vapor has two important characteristics or influences to radio waves in the atmosphere. It attenuates it and it delays it. And if you have, in this case, an observation of a celestial source from physically separated observation points, as is commonly used in very large baseline interferometry, you need to know what the delay is so that you can calibrate your correlation in your imaging afterwards. So how do we measure this water vapor radiometry? Well, this water vapor, well, through a process of radiometry. I won't get into the details of black body radiation, hyperfine transition lines tonight, but suffice to say that these gases, atmospheric gases, have specific profiles for emitting noise, which matches their absorption characteristics. So if we put up a very sensitive microwave receiver targeted at one of these emissions lines, in the case of water vapor, it's 22 and 183 gigahertz, and we measure the noise in the specific band, we can get an estimate of the concentration of water vapor in the atmosphere or in the scene that we are observing. So we're just measuring noise in a fancy way. So water vapor radiometers, they exist, they have existed for several decades. Why do we need new and better ones? They're usually quite big, and they're big because of the way that they're constructed. You can see here the typical worm feeds, waveguides, power modules, driver modules. A lot of the size is actually attributable to the way that we assemble it. Also due to the fact that many of them contain moving parts, because one of the calibration steps in these radiometers is that you tilt your beam from zenith down to about 30 degrees above the horizon to calibrate the instrument for a specific observation. And it works for a fixed site where you just want to monitor the site on a day-to-day basis to manage your performance on the site. But if you want to deploy a small, lightweight unit for long-term site surveying in a remote location, this idea is out. It won't work. And I know it won't work because we've had to replace and repair many of these components over the years in this particular machine. So the question is, can we create cheap, low-cost, compact, integrated water vapor radiometers? And we've made great strides towards this. One of the first things we had to contend with is that these water vapor radiometers are notoriously difficult to simulate, because you need fast time steps to cover the frequency range, but you need many time steps to evaluate 1 over F noise and integration time. So coming up with new ways to simulate these radiometers in an efficient way was one of the first things we did working on this problem. We've produced several sample designs. There you can see the single board integrated radiometer, and you can compare it with the modular integration we have here. So we've had some success in this regard. Version 2 here as well. We've designed a single chip version, though we didn't get around to prototyping it. And we also figured out that the same kind of modular single board approach can work for other kinds of radiometric receivers. So this is an example of one we're currently qualifying, which is a image rejection receiver giving us 2 radio astronomy observation bands at K-band simultaneously at 2 different IF outputs. The last topic I want to illuminate tonight is our work on reliability and built-in self-testing. Many years ago, we started with a radiometer to look at solar radiation from a satellite platform, a millimetre wave radiometer. And we asked ourselves, well, what will go wrong with this design once we launch it? And there are the obvious things: shock and vibration, thermal cycling, but the one we identified as the greatest risk was total ionizing dose radiation. And so we asked ourselves, okay, how can we model this degradation at millimetre wave frequencies, and can we measure this degradation in situ? So we've done a couple of experiments on single transistors biased difference conditions at millimetre wave frequencies, and we found things that we expected and things that we didn't expect. The one we expected was a reduction in gain, which was lower transconductance in the device. We expected that. What we did not expect to see was an increase in the parasitics in this model. And that's an important observation, as you can see from our follow-on experiment, where we applied it to an amplifier response at 60 gigahertz. The gain of the amplifier reduces, as explained by the lower transconductance. But the other important effect is that the bandwidth of the operation narrows as well. This we can attribute to the increased parasitics. So whatever measurement system you implement has to work for both frequencies. It's not good enough to check only the performance in the middle of the band. You have to evaluate what the performance is over the full bandwidth of operation. For that, we looked at a technique called oscillation-based built-in self-testing. Very briefly, I want to introduce the concept. Any device under test, with sufficient gain and the right kind of feedback phase will oscillate if you connect it in such a way. And by monitoring that oscillation, you can tell something about your gain path under the assumption that you know what your feedback path is. That's very well characterized, and typically it is. So what are the advantages of using this technique to test RF electronics? Well, the first thing is you don't need an RF source to apply to your device for the test, because the device is its own test source. And if you use the correct kind of interpretation of your oscillation, you don't need a down converter or digitizer at RF frequencies either. You don't need to test a surrogate, as is often done in these systems. You can test your active device as it is used in the system, and you can use a technique to access inaccessible nodes in system or inaccessible systems. It also has advantages in production testing, where you don't need to put an RF signal on your chip to test it, and if you do it right, you don't need to extract an RF signal from your chip to measure it either, which vastly reduces the cost of testing. So we've made contributions to the theory of oscillation-based testing. We demonstrated the first concept design in 0.35 CMOS, a 2.4 gigahertz low noise amplifier. We could demonstrate that this test methodology works despite typical process, supply rail voltage, and temperature variations. We could define a new figure of merit for this test, which allowed us to compare different test strategies for the process. And we can demonstrate that we can apply true built-in self-testing without down conversion digitization, using only power detection. We also looked at OBT at lower frequencies, and we found a couple of interesting things. The one was that we could use machine learning and artificial intelligence to estimate where a fault is in a circuit. But what we found interesting was that many of our good results we got not from monitoring the steady state performance, but by monitoring the transient startup of the oscillation. And that's interesting, because if you have a power detector at RF frequencies and you're only interested in detecting the envelope of your oscillation, then you get a very low frequency signal which tells you something about the performance of your device at very high frequencies, without the need for down converting or digitizing that high frequency oscillation. We've since implemented the same idea into a discrete component design in RF PCB, also a low noise amplifier. Again, it does not use down conversion. And here we identified a new test mode, the self-quenching test mode, that generates that slow time varying response that we can digitize when we can't digitize the high frequency oscillation. We've also applied this to a first iteration of a system test, where we used our low noise amplifier that's oscillating as a test source to drive the rest of the system to show out problems along the system chain. Given all this, the obvious question is, you've kept yourself busy for the past 10 years, what are you going to do for the next 10 years? As I said at the beginning of this talk, the trend is higher frequencies, wider bandwidth, and that is where our next research challenges will lie. Taking what we've learned at 2.4 gigahertz and 60 gigahertz and making it work at 300 gigahertz and a terahertz eventually. I believe there is a role to play for single integrated circuit receivers in radio astronomy, especially for aperture array receivers, and that is something that we will pursue actively along with our work on single integrated circuit integrated radiometers. I want to explore new ways of producing these systems and assembling them using a combination of subtractive and additive methods, applying each to its strength to the ultimate benefit of the user and the producer of the system. And then, of course, see if we can't get to a point where we can fully integrate and assemble a system using only additive manufacturing. to conclude, going through a career like this is an opportunity for introspection, but certainly one of immense gratitude to everyone that's played a role in your career to this point, and none less more so than the students I've had the privilege of working with. This cartoon illustrates my view on student supervision. It is not the task of the study leader to walk the jungle with the student. It is their task to survey their position and to guide them towards a goal. And as part of that, they don't always experience the snakes and the toe stubbing and all the other challenges that the poor student faces under the jungle canopy. So, to all of the students that have stubbed their toes and tread on snakes and under the jungle canopy, in support of the research we've done together, thank you. Thank you very much for your contribution. It has been an honor and a privilege to work with each one of you. To my co-workers and my collaborators as well, some of them who are here tonight, without your insights and unique perspectives on the problems that we face, none of this would have been possible either. So thank you very much for your contributions as well. These are people that are often overlooked in research, but the right supplier who can put the right component or the right test equipment in your hand at the right time, at the right price, is invaluable to research, especially to equipment and prototyping intensive research as we do in our lab. So to our suppliers, many of them are here tonight as well, thank you as well for the contribution that you've made to the success of my research over the past years. As the suppliers will confirm, what we do is incredibly expensive. So to everyone that has supported our research financially or in kind as well over the past years, our funders and our industry partners, some of them are here tonight as well, thank you very much for your contributions. Whether it's an 8-hour day or a 12-hour day or sometimes a 24-hour day, eventually you have to go home. And it is the love and the support of the people that meet you there that give you the strength to go back the next day. To my friends, my family, especially my loving wife, who has, as you can see from the pictures, quite literally followed me to the ends of the earth for this job. Thank you very much for your love and your support. Without you, I would not have been here tonight. And thank you to all of you for attending tonight.
Thank you very much, Prof. Tinus, for the way that you spoke about the challenges in micro and millimeter wave design, frequency, range, innovations, and everything that goes with it tonight. And thanks for providing a clear and, I added the word here in my notes, mostly understandable version. Because I have to admit, as a civil engineer, I look at a lot of this and I say, wow, our disciplines are not the same. But I could follow most of it. And it's interesting the way that you explained and that you spoke to link the complex challenges to normal life. And I would like to link to something that Prof. Maharaj alluded to, the way that you focused our attention to what we are good at, which is important, the real in-depth, high-tech understanding of the fields and the complex phenomena that we are working at, but how that support our contribution to society in terms of what we are good for. Because if all of the graphs and the details that you showed us tonight did not have the practical side of so what, then I would endeavor to say, and it's difficult to say that from a high-level research university, it may have been slightly useless. Because if we don't contribute to society, all of this gets to a point of, wow, that's beautiful, but what do we do with it? And thanks for linking that to the bigger picture. I think you also quite clearly highlighted why the students that's in the audience, as well as future students, has got a lot of work still to do. The work for sure has not been completed. And lastly, I think also, although you did not mention it explicitly, in this case, was that the need for human brains and experiences are still really required. So in a world, again, linking to what Prof. Maharaj indicated, where if you look at social media, it will tell us that generative AI is going to make all of us useless without a future. I don't think ChatGPT can do what you've done. I think it will be a while. But it's quite important to always look at that part of what we are busy with, because some of the stuff can be done much quicker and easier by various techniques. And I think we will be short-sighted if we don't make use of that. But that we look at the challenges of where's my human interaction, my understanding, my connectivity really required. And lastly with that also the highlights in the transdisciplinary aspects of the work. Obviously with the 3D printing and the materials, but I've also seen some of our other colleagues in the School of Engineering's names in some of the publications. And obviously that also links to the world that we are working in, where we are not just focusing on one specific detail discipline at a time and think we can solve the problems of the world. So it's really my wish for you that you've still got great success in future with your endeavors. I hope it all runs well. With that, ladies and gentlemen, it's my privilege to thank Prof. Maharaj for your participation this evening. Also, having been connected to this department for many years, still quite interested in what they, as well as the faculty, is doing. My thanks and appreciation to the EBIT team, Managa and Suzanne, for arranging everything. As with all functions like this, there's many years of preparation on Prof. Tinus' side, not just a month or so, 15 years plus of preparation, but there's also the preparations to put everything together. And Managa, Suzanne, your team, thank you very much for that, what you have done. Please be on the lookout and remain on the lookout for our further inaugural lectures. We've got another 3, I think, to go for the EBIT faculty. And obviously there are others also from the other faculties. And I think it's important for us to also understand that sitting in inaugural lectures from other faculties sometimes ignite thoughts in our brains that we did not have before, because we start to see a bigger picture in terms of what's possible. So please be on the lookout, especially our colleagues from industry and so on, and be welcome to support us also in those fields that we all know slightly less of. With that, ladies and gentlemen, it's my pleasure to invite you, once we finish the official proceedings now, for refreshments in the foyer area, and I hope that you've got a safe evening and safe travels back home. Will you please stand and remain standing while the procession leaves the hall.